Okay, as promised, I'm going to start chapter 2. I can't guarantee how far we'll get, but I want to at least get into some of chapter 2, as that is what we're supposed to be covering this week. I was hoping we'd get further along, but life is what life is. Unfortunately, we cannot just stop because of snow. I have X amount I need to cover in Y amount of time, so we'll get what we can get. Okay, so chapter 2 is where we start to look at atoms, periodic table, and kind of how we know what we know, kind of the history of the science. Idea is that if we see farther than most, it's because we stood on the backs of giants. So, first, hopefully we get at the same spot that we all understand that chemicals are represented by our symbols. Each element is represented by a 1 to 2 letter symbol abbreviation. That certain elements, it's really obvious to see why they're named what they are, but certain elements are abbreviated based on their ancient name, whether Latin or Greek. These are the names. So antimony is Sb, even though there's no S or B, because it was originally called stibium. Gold was aurum. Iron was ferrum. We still refer to iron as being ferric in nature. So lead is plumbum. You might have a plumbob. But mercury was hydra hydrargyrum, potassium calcium, argentum, which you can still get like argentium silver, natrium, stannum, wolfram. So some of them are going to be obvious, some of them are not so much. But generally speaking, when we combine these multiple symbols together, it will represent a chemical formula for various compounds. We'll use subscripts on those compounds to represent the relative number of each element in there. So if it's CO2, that subscript of 2 tells me there's 2 oxygens present, the compound of carbon dioxide. As opposed to CO, no subscript, it's 1 carbon, 1 oxygen. Now, what makes science so special is we have certain fundamental laws that will allow us to do the science, the reproducibility. If we didn't have these fundamental laws present, there's a lot more nonsense that'd be going on. We could not really reproduce any results. I mean, as it was, you may have heard of alchemists in the past. The idea of these early proto-scientists mixing things together to try to find the philosopher's stone, something that would turn lead into gold, things that would grant immortality. That these were the early chemists mixing these compounds together, lighting them, burning them, doing all sorts of reactions to find new compounds. Well, depending on how well they did these science, these are all going to be controlled by these fundamental laws. That if these weren't hold true, then you couldn't do the same experiment twice and get the same results. But those fundamental laws are the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. The conservation of mass just says that matter is neither created or destroyed in a reaction. It will only be transferred. So if I start with 5 grams of reactants, I should have 5 grams of products. It doesn't matter if it's 5 grams of the desired product, it's still the total amount of product should weigh the same as what I started with. Now they may be converted into gases, which are harder to weigh, but it's still 5 grams worth of gas. That is the key here. The law of definite proportions means the proportion of each element is constant within a given compound, which will lead to a constant percent by mass. If water didn't weigh 18 every time, we would have trouble calculating this law of conservation of mass. But water contains one oxygen, which weighs 16, and two hydrogens, which are one each. 16 plus 2 is 18. So if it's not 18 and doesn't have the same 2-to-1 ratio, things would get very dicey. But to calculate the percent by mass, a percent is just a small thing divided by total times 100. So percent by mass is the mass of a given element divided by the total mass times 100. So methane, the amount of hydrogen, is 25%. Methanol, which adds an oxygen to methane, the amount of hydrogen goes down because even though the amount of hydrogen is still 4, the total weight has gone up. Ethane, which is a C2H6, has a greater percentage, well, actually a lower percentage of hydrogen, because now for every one carbon, there's 3 hydrogens instead of 4 for every one. So different compounds have different percentages. And the law of multiple proportions simply states that elements will combine in simple whole number ratios when they form a compound. So one methane molecule, and 2 oxygen molecules will react to form 1 CO2 molecule and 2 water molecules. You're not going to get a half of a molecule. If I do methanol, you need 2 methanol molecules and 3 oxygens to get 2 CO2s and 4 waters. If I did it with any lower number of combination, you would have half of an oxygen molecule in order to make that work. So the idea here, though, is these were not immediately known. These had to be developed over time through thousands, maybe millions of experiments, people taking rigorous notes on these things to find out these are always holding true, because it's essentially a black box of science until we start to develop these rules and we got someone to create a theory that kind of explains this. Then it's suddenly, they kind of snap into place. We see this happen, and then we try to make a hypothesis and build on this into the theory. So our first scientist we're going to discuss is John Dalton. His theory will explain these fundamental laws. One, that he claims that matter is made up of very tiny, indivisible particles called atoms. He's not the first person to come up with the idea of atoms, but he's the first person where it has legs. There was a Greek who created an atomic theory in opposition of the Aristotle's, or was it Plato's, 4 elements: the fire, earth, wind, air, and water. But it was not nearly as developed as this. But the idea is, tiny indivisible particles called atoms. Each atom of a particular element has the same mass. So every carbon weighs the same, but the mass of one atom of one element is different from the mass of one atom of another element. So carbon may weigh 12, but oxygen weighs 16. Hydrogen weighs 1. So each element has identical mass, but different elements have different masses. Atoms will combine to form what we call molecules, and they will combine in simple, small, whole number ratios. And then atoms of some pair of elements can combine with each other in different small whole number ratios to form different compounds. So we can essentially rearrange, and they will not. We're just exchanging atoms, and the masses essentially stay the same. Now, these four statements are pretty simple. And at this point, we may be thinking, yeah, no duh. However, remember, atom is still a hypothetical idea. We have not seen the atoms. It would make sense if atoms existed, though. We have not. They're still working on the macroscopic scale. They're not able to break things down to the atomic level yet. We don't have an electron microscope. We don't have all these cool things that we have now. And even then, the theory is not fully correct because we know now atoms are indivisible. Atoms are divisible. Atoms are made up of protons, neutrons, and electrons. And even those guys are divisible into quarks and gluons and all that fun physics stuff. But the idea is that this had not been proven incorrect, and it helped stimulate research in this field. That if we have these rules and this kind of makes sense, everyone can start to go, this works with my data. This works with my data. All this data they have would be properly explained if this theory were to hold true. Because for the most part, when we do our reactions, we are not dividing the atoms. We are not splitting them up. We are just transferring atoms. So from there, people start to probe the nature of what are these atoms? How can we better understand these atoms? And so they start finding the evidence of subatomic particles. Some of these subatomic particles have positive charge, some have negative charge. Keep in mind when we consider this positive and negative charge, similar charges will repel, much like a magnet. Opposite charges will attract each other, like a magnet. So positive and negative attract. Positive and positive will repel. Negative and negative will repel each other. Just like you could put two opposite poles of the magnet and they will stick. If you flip the magnet around, suddenly it won't stick. It will repel each other. So around the time they found a way to create what's called a cathode ray tube. It's a glass tube where we put two wires into either side of this glass tube, and we pull a very strong vacuum on it. So we basically evacuate this tube of all air, or most of the air, and we connect these two wires to a power source. So when they do this, they put the wire through the tube. They notice the tube begins to glow. It fluoresces. Now, this was due to the idea of invisible electrons called cathode rays, because when you hook up a voltage to a battery, the cathode is the negative side, and so it's shooting out the electrons from the cathode. And they're being attracted to the anode. So they called these electrons cathode rays at the time, thus the cathode ray tube. So when these cathode rays hit the glass would glow. And so these would constantly be flinging all over the place, yada, 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 and hit all over the glass. People doing all sorts of weird experiments with this. Like, let's stick this object in the cathode ray and see what happens. Well, if you stick an object in, it absorbs all the cathode rays, and so you have a big spot behind it where it's not going to glow because it's acting as a shield. Glass blowing was a real big thing back then, so you could blow the glass into unusual shapes and do all sorts of neat experiments. What they found is if they didn't pull the vacuum, no cathode rays. That's because if you didn't pull the vacuum, you had a bunch of air. A bunch of air in there is going to absorb all these electrons. They're not going to be able to hit the glass. It's not going to be able to glow. Basic idea here. Now, they found these cathode rays could be deflected using a magnetic field. They were attracted to magnets, so we could make it swing one way or another. We can also apply an external electrical field, and they would also be deflected in a similar way. So, one guy, J.J. Thomson, went out to try to understand these cathode rays. So he wanted to apply two opposing fields, electrically charged plates and a magnetic field. And the magnetic field is a constant magnet that's going to deflect it one way, and the electrically charged plate was a variable field where he's going to essentially vary this. And what's going to happen is one's going to be pulling it one way and the other's going to be pulling the other way. And essentially, he was varying the field till he found at what point did the electrical field cancel the constant magnetic field. If one was out of balance, the electron beam would fling out to one side or another. But if he managed to cancel each other out, they would reach the end without being deflected in the least. And by playing around with those two fields, he was able to find the charge to mass ratio of the electron. That there's a certain amount of essentially how much charge, how much attraction could it feel, as opposed to how much mass, so essentially how much momentum it had. So essentially it shot through the little pinhole to keep it just a single electron at a time, and then deflected it and see which one is perfectly countered. Now, with that in mind, I used some of the pictures from the book, but this one, they had a video. I didn't want to try to embed a video in here. But so, Robert Millikan goes on to create his oil drop experiment, where he's going to measure the charge of the electron. He wants to do this. So, what he does is he generates a bunch of oil droplets, using like a little perfume bottle, sprays these oil droplets into an evacuated oil drum. So these droplets are going to float and eventually fall and be funneled through a tiny little hole in the drum. Now the hole allows them to go drop by drop through, and they get struck and excited by X-rays. So when they get struck by X-rays, they're given charge. They're given charges. Now, it may not be just one, maybe multiple charges, but the fact that there is some ratio of charges on these guys. And he's going to then, using a little viewer that allows him to see into this vacuum-filled drum, he's going to apply a electrical field to these different plates. These droplets are going to be attracted to the upper plate and repelled by the lower plate based on what charge he may apply. By controlling the strength, they can float, even rise up. And by looking at drop by drop, he's able to figure out, okay, at what point is it completely canceled by this electrical field? And so the idea being, if he knows the mass of a droplet, which is going to be how much gravity is being pulled down, he can figure out how many charges are present and the effect of each charge that's going to oppose the gravity pulling down. So by doing that, he can determine the electrical field strength of the droplet at 1.602 times 10 to the negative 19th coulombs. Now, do I expect you to know that? No. Don't worry about that. But he finds the charge of a droplet. Now, because our dear friend J.J. Thomson had already found the charge to mass ratio, we can now derive the mass of an electron, which would be 9.10 times 10 to the negative 28th grams. Really small mass. Now, because they knew atoms were neutral, and if an atom were to contain a negative charge, it must also contain equal amounts of opposing positive charges. And it should have the same charge so as to cancel its out. Now, they also knew that the proximate mass of an atom, they could figure out, well, what's the lowest number ratio of this given atom? And so they know that based on the mass of electron, that's way too small. So the majority of the mass must come from the proton. Even though it's the same charge, it contains much more mass. So they were able to figure this out. So at this point, atoms are still a mystery, but we did know a few things about them. We knew that they're neutral charged. They have a decent amount of mass. The majority of the mass must be proton because the electrons are very small. So John Dalton previously hypothesized that atom was indivisible sphere, so this picture. But J.J. Thomson, with breaking that up into the atoms of neutral with the positive negative charge, predicted it's a largely big chunk of positive with small little negative negative electrons sprinkled throughout. So, you imagine this atom as what we call a plum pudding of positive charge, where the electrons are the raisins within the pudding. This is known as a plum pudding model. It's a little silly of a model, but sometimes that's what we have to work with. Now, the reason why we talk about this is because even smart people get things wrong sometimes. So there's around the same time, nearly the same time, radioactivity is being discovered. People are finding out that, oh, hey, certain elements will generally fission off various radioactive particles. We can give off electrons shooting out, alpha particles shooting out. We have people like the Curies, got Rutherford Hayes, and so we found out that certain elements will give off alpha particles. Alpha particle is a highly positive particle containing 2 protons and 2 neutrons, essentially helium nuclei. So Rutherford and his associate Hans Geiger, Geiger counter fame, wants to go test the plum pudding model. He's going to analyze the scattering pattern of shooting these alpha particles at a thin sheet of gold foil. So it's going to fire like an alpha particle sniper rifle shooting at the thin gold foil. The idea that because gold is very heavy, but it can also be created into a very thin sheet, it's very likely that the particles will puncture through and get to the other side. So he uses radon gas as his alpha emitter, shoots alpha particles out, and uses a circular fluorescent screen to measure where alpha particles are hit. Just like X-rays, radioactive material, when it hits a photographic plate, it darkens that plate. The X-ray works because your bone absorbs all the radiation and the plate stays white. Your skin does not absorb the radiation. The radiation pierces through, and so that darkens the plate to be black. So dense objects will absorb the radiation, while thin objects, they can punch right through and we'll see just it darken the black. So the idea was he shoots his alpha particles through, and it's going to go through the foil and just hit the screen on the other side. Now, there might be some deflection, and you're like, well, shouldn't the positive nucleus and the positive plum pudding and the positive alpha particles repel? Well, the idea was, if this is truly a plum pudding, that the the positive charges would be so well distributed that it's thin and the alpha particles could punch right through. It's like wearing leather body armor to try to block a bullet. It's like, well, it might work for weak bullets, but like a sniper rifle, it's going to punch right through like nobody's business. There might be some deflection, but that's not going to be very well. Oh, it's not going to block very well. So, here's what they thought would happen. Some particles would punch through without a problem. But see, the thing is, they looked at the whole screen, and that wasn't the complete story. While some particles did experience little to no scattering, it managed to slide through without hitting any atoms. But some particles received intense scattering, where they hit and bounced off to the right, to the left. And some hit and bounced straight back. So you see right here, it hits this and bounces all the way back. Because the scientists didn't just look where they expected the answer to be, but they looked at the whole picture. They found that what they thought we were going to find is not the case, because they went in with an open mind and analyzed the whole film. They found these unusual scattering, these bouncing back. So, the plum pudding model could not explain why these alpha particles would bounce back. If this is such a mucky pudding, if you shot a bullet at a pudding, it would just punch right through. You would have the only way to bounce something back would be a very dense positive object. A very dense positive object. So essentially a proton hitting another proton would reflect it. But if it was widely distributed, it should punch right through. So with that in mind, Rutherford developed the nuclear model of the atom. Now, the nuclear model of the atom is a hypothesis that essentially has these basic premises. The atom's positive charge and the majority of the mass is located in a relatively small area, which would be called the nucleus, thus the nuclear model. Plural of nucleus is nuclei. The vast majority of the atom is empty space. Small negatively charged electrons are spread throughout this empty space, the electron cloud. The number of negatively charged electrons are equal to the number of positively charged particles called protons, which are inside the nucleus. So, the majority of those alpha particles pass through electron clouds without hitting the nucleus. Occasionally, some of those alpha particles might hit a glancing blow on the nucleus and thus ricochet off. And occasionally, some of them would hit it dead on, and thus they would see that back scattering. But because most of the atom is empty space, a lot of those alpha particles pass through without scattering. Now, as I said, scientists knew something about the expected mass of an atom. They found that the mass didn't correlate with the number of protons that they found, because they had an idea of how many protons are in an atom as well. So Rutherford went on to postulate the presence of a neutron, an uncharged particle but has a similar mass to the proton that must be present. And this wouldn't be discovered many years later by James Chadwick, which was one of Rutherford's students. That essentially they found by bombarding this atom with radiation, we get these weird particles that shoot off that are not deflected by magnetic fields, so they're neutrally charged. So it's like, this must be our magical neutron. But that's neither here nor there, so that was discovered much later. But just saying, This is a sign of a good hypothesis, a good theory, that you can postulate the presence of something that's there long before you can actually find it. So with that in mind, here are some simple atomic facts. Atoms are made out of protons, neutrons, and electrons. The generalized charge of a proton is +1, electron -1, neutron 0. The atomic mass in atomic mass units of a proton is a little bit greater than 1.073. Neutron is 1.0087. See, very similar. And the neutron is a small fraction. Not 1/10, not 1/100th, not 1/1000th, but a half of a 10,000th of a mass unit. So really, they are almost inconsequential when it comes to the mass. Each element is going to contain a different number of protons, which we're going to call the atomic number, Z. The number of protons determines the element. Every carbon atom will always have the same atomic number of 6. If it does not have 6, it is not a carbon. Nitrogen will always have 7. Oxygen will always have 8. This is always going to hold true. If it doesn't hold true, then it's not the same compound. Now, a neutral compound will have equal number of protons and electrons, but not all atoms will have the same number of neutrons. Atoms that contain different number of neutrons are called isotopes, Greek for at the same place. But so hydrogen has 3 known isotopes: protium, deuterium, and tritium. They all contain 1 proton, but they contain either 0 neutrons, 1 neutron, or 2 neutrons. So protium contains a mass of 1. Deuterium contains a mass of 2. Tritium contains a mass of 3, because 1 plus 2 is 3. So the idea is that their mass changes, but they're still hydrogen atoms. Isotopes can be distinguished by comparing the mass number, which is A. The mass number is simply the sum of the protons and the neutrons. An isotope can be expressed through its atomic number, its isotope symbol. So, writing a generic way of an atom, we have the element symbol, the atomic number A, or say the mass number A, and the atomic number below Z. So we'll finish up, and maybe with a practice problem in a minute. Now, not all atoms have to be neutral. Some atoms will become charged particles called ions. An ion is generated when we lose or gain an electron from within the electron cloud. The proton and neutron count will not change in our chemistry. If we look at nuclear chemistry, then things can change, but the majority of chemistry will be due to the loss or gain of electrons, because the electrons are out in the cloud. It's very easy to remove them or add them. The nucleus is very hard to get at because it is incredibly stable. So when an electron is lost, an electron is negatively charged. So when we remove a negative charge, we get a positive ion called a cation. When electrons are gained, we are adding a negative charge to something. So it becomes an anion. So when we write these charged particles, we're going to add a superscript behind the element with either a positive or negative charge, which is going to be talking about how many protons we have in comparison to the electrons. So it's the difference between protons and electrons. When we have more electrons, we get a negative answer. When we have less electrons, we get a positive answer. So, this last thing, we'll finish up with this practice problem, and that's where we'll go. These first 4 molecules are all neutral. So that means they have the same number of protons as they do electrons. So lithium, number of protons is 3. The number of electrons must also be 3. The number of protons, the number of neutrons is the difference between the mass number and the atomic number. So we have 3 protons, the mass is 7, so it must have 4 neutrons. Chlorine. Chlorine is neutral in this case, 17, so 17 protons. It must also have 17 electrons because it is neutral. The mass number is 35, so to make up the difference in mass, we must have 18 neutrons. Now, what's not shown here is that there is another common isotope of chlorine, which is chlorine 37. So if this one contains 18 neutrons, the isotope contains 20 neutrons, because 37 minus 17 is 20. Phosphorus, neutral, 15 protons, so it must have 16 neutrons. Carbon, it's neutral, so 6 protons, 6 neutrons, and 6 electrons. Now, potassium, charged, potassium cation, charged. So it must contain 19 protons. That's still going to be true. 39 minus 19 is going to be 20 neutrons. It is positively charged, so positive 1 equals 19 minus the number of electrons. So there's 1 less electron than there is protons. So 19, there must be 18 electrons. Now, oxygen anion. We have 8 protons. We have 8 neutrons, but we have 2 extra electrons. So if we have 8 protons, 2 extra electrons would put us up to 10 electrons. And lastly, iron cation. Well, we have 26 protons. We have 30 neutrons because 56 minus 26 is 30. And we have 3 fewer electrons. 3 fewer electrons, so 3 fewer than 26 would be 23 electrons. So that will be where we will stop for now. But be able to do some of this simple stuff. If I give you some ions, I want you to be able to at least tell me the proton, neutron, and electron count if I give you something like this, because it's really easy to do if you take the time to learn it. It's easy problems. Have a good day.